In CaseL, we're going to be taking a look at machine breakdowns. This is a fairly realistic problem that you might get from the real world, but probably, well, it's certainly not something I can ask for on an Engineering 310 exam, but it's useful to see how one of these cases might actually work. But it's still a goodness of fit test that you'll be able to understand now. So in this one, we're going to have a figure shown on the next slide that shows the data of the time intervals between breakdowns of a machine. Is there any evidence that it is not reasonable to model these intervals as the exponential distribution with a mean of 5 days? Well, the mean of 5 days is giving us our parameter for the exponential distribution. By the way, that's the same parameter as you're used to for the Poisson distribution. So what this basically saying is that lambda is equal to 5. We're going to use that parameter to see if it's reasonable to call the time between breakdowns exponentially distributed. Next, we have the actual data. This is the time intervals between delays that had been observed, and that's the actual distribution of observations. And then we now need to categorize and decide what time intervals we're going to use. Nobody says that we have to use equally sized time intervals, and we won't, or we wouldn't be able to solve this problem successfully. In fact, we have some choices in how we divide up our time axis. If I divide the time axis into the categories of 0 to 0.45, 0.45 to 1.05, 1.05 to 2.05, etc., I can then use the exponential distribution, which I won't cover here, but you can just look up the formula for the exponential distribution and get the expected number there. We divided up our data into those categories and can report the observed number, and that allows us to calculate each one of the chi-squared statistics for each class or each category, and I've done that and summed them here. But notice, if you look at that bottom class, the expected number is 4.38. That violates one of our rules that said the expected number always has to be 5 or more. So because I did that, I'm going to combine those bottom two categories and actually just have one category that's greater than 10.05. So I've just combined the next two in the next column. And what I need to do is I've got my chi-squared statistic and it's not very big. So if I want to test the null hypothesis that these are exponentially distributed with a mean of 5 against the alternative, no they're not, then I just need to compare that chi-squared statistic to the critical value. I should probably use an alpha of 5% to keep a nice balance between type 1 and type 2 errors. But I next need my number of degrees of freedom. How many categories do I have in the rightmost column? 1, 2, 3, 4, 5, 6, 7, 8, 9. So I have a number of degrees of freedom equals to 9 minus 1. When I look on the table for the case of degrees of freedom 9 minus 1, or 8 degrees of freedom, and an alpha of 5%, I get a critical value of 15.51. And our chi-squared was much less than that. So we're going to have no reason to reject the null hypothesis, and they do seem exponentially distributed with a mean of 5. So that's one way of solving this problem. But we actually had a lot of choice in how we did this, and you might instead pick different class sizes. In fact, I didn't like having to combine those bottom two categories, so I would redo this in a new way. I'd use the interval from x1 to x2 being 0 to 0.5, 0.51 to 1, 1.01 to 2, etc. And notice by using these classes, when I look at my expected numbers, all of them must be 5 or more, and I've achieved that. So with this result, I have a better balance between different categories or different classes, and I got my chi-squared statistic that sums to 5.26 essentially. Let's compare that to our new critical value. To get the critical value of chi-squared, we need to count the number of categories and get the degrees of freedom. So how many categories here? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So we have 10 minus 1 degrees of freedom. So 10 minus 1 degrees of freedom, or 9 degrees of freedom and a alpha of 5%, gives us a chi-squared of 16.92, and our chi-squared was much less than this 16.92. So again, with this the second way of looking at the problem, we also have no reason to reject the null hypothesis that these are these, and in fact these do appear to be exponentially distributed with a mean of 5 days between breakdowns. So that's case L and our last example problem from this module.